In this lecture, we're going to discuss a third type of elimination reaction known as unimolecular elimination conjugate-base reaction, also known as E1cB. Now, E1cB is similar to the E1 reaction in that there are two different steps taking place. However, unlike in the E1 reaction in which our leaving group dissociates in the first ionization step, in the E1cB, we have our deprotonation step taking place. In other words, our nucleophile acts as a base taking off this H ion, leaving this pair of electrons on this carbon, forming a carboanion. So instead of forming a carbocation as we do in the E1, in the E1cB, we form a carboanion, so a negative charge on the carbon. In the second step, this same lone pair of electrons attacks this carbon, forming a double bond, a pi bond, displacing this bond along with our leaving group. So we form an alkene just like we form in the E1 reaction. Now, under which conditions will an E1 take place, and under which conditions will an E1cB take place? Well, if we have a very good leaving group, that means this leaving group will be able to readily dissociate. And so if this can readily dissociate, we're going to have the E1 reaction. But in order for the E1cB to take place, we must have two things. This must be a poor, a bad leaving group, and this carbon H bond must be a weak bond. In other words, it must be easy to take off this H atom. So once again, let's review. In the first step of this E1cB reaction, an H plus ion is removed to produce a carboanion. In the second step, the lone pair of electrons on the carbon displaces our leaving group, forming an alkene. Now, when will an E1cB reaction take place? Well, one, an H atom that can be lost easily, and second, we must have a poor leaving group. Now, when we spoke about carbocation stability, we said that as we go from methyl to primary to secondary to tertiary, our stability of the carbocation increases because we have more hyperconjugation taking place. Now, it turns out for carboanions, the opposite effect is true. In other words, as we go from our tertiary to our secondary to primary to methyl carboanions, our stability increases. Why is that? Well, now when we no longer have hyperconjugation, now we have the solvent playing a role in stabilizing our carboanions. So in order for our solvents, such as water, for example, a polar protic solvent, in order for the water molecule to stabilize this carboanion, the partially positive charged H atoms must be able to get to this carbon with a negative charge to stabilize it, so that we have electrostatic interaction between the negative and positive charges. But in order for the water molecule to get to the carbon, these groups, side chains, must be relatively small. And notice as we go from this tertiary to the methyl, our groups get smaller and smaller. So as we go from right to left, our water is more able to get to the carbon to stabilize it. Once again, methyl carboanions are easier to get to by the polar solvent because they're less sterically hindered. And we see it going on here. In this tertiary carboanion, the water molecule cannot get to this carbon because it's too sterically hindered by these side chains, by these relatively large side chains. At the same time, these relatively small H atoms don't really interfere. They don't block the water molecule from getting to this carbon. So in this case, we have a lot of stability. In this case, we don't. And that's exactly why, as we go from tertiary to methyl, our carboanion stability increases. It's because of our polar solvents, such as water. Now, let's discuss a second type of important concept known as Hofmann elimination, and this is related to carboanion stability and the E1cB reaction. So, what exactly is Hofmann elimination? Well, in Hofmann elimination, the less stable, less substituted product is the major product. Recall when we spoke about Zaitsev elimination, we said that the major product is the more stable, the more substituted alkene. In other words, if we have the following reaction taking place, we have a base and we want it to undergo an E2 reaction, with this setup we're going to get the major product to be the less stable product. The more stable product will be the minor product. Why is that? Well, in order to answer the question, we have to examine our mechanism, and in our mechanism we have to look at our transition state. So there are two H atoms that this base can take off. It's either this side H atom or this H atom between these two carbons. Which one will lead to which product? Well, if this H is taken off, this will be produced. If this H is taken off, this minor product is produced. It looks like because this major product is produced, this H is more readily taken off. Why is that? Well, to answer the question, let's examine our transition state. In the transition state of our E2 reaction, our base, let's say some hypothetical base B with a lone pair of electrons, takes off or begins to pull off this H ion. As this H ion is being pulled off, the lone pair of electrons is getting closer to this carbon. As the electrons get closer to our carbon, a partial negative charge is formed on this carbon. And that means we form a carboanion. Now, if this H atom was taken off instead, we would have a more substituted carboanion formed. Remember, the more substituted our carboanion is, the less stable our carboanion is. So in this case, we want the more stable carboanion, so we want the less substituted carboanion. So this is what we get. This develops a more stable, less substituted carboanion, and therefore this H atom will be more readily taken off than this H atom, forming our major product, which is the less substituted, less stable product.